What's up, you guys? Almost heaven, West Virginia, Blue Ridge Mountains, Shenandoah River. Life is old here, older than the trees, younger than the mountains, flowing like a breeze. Take me home, country road, to the place I belong, West Virginia, mountain mama. Take me home, country road. All right, how's it going, you guys? That got a little high for me, I'll be honest. So, welcome, you guys. We're going to talk a little bit about nuclear chemistry here, and really, this is our last new topic before we get going on. Ooh, that was a close one. Before we really just start reviewing, we've covered most of the information that you need to know. So, yeah, and we'll talk about this. And this may get split into 2 videos. I'm not sure. Depends how fast I can move through stuff. So I'll try and move somewhat quickly without losing you guys. So we're going to talk about structure and energy, okay, nuclear decay and stability, and then last but not least, nuclear fission and fusion. Here we go. All right, so just a quick review, the nucleus, you guys. The nucleus contains protons and neutrons, okay? We know this. These are known as nucleons. So we refer to these in nuclear chemistry as nucleons. And I think you're familiar with this notation, but let's just make sure. We've got uranium, right? Okay, that is our element here. On top, we have the total mass of this atom. So that means all of the protons and neutrons added together gives us our total mass. On the bottom, this bottom number tells us the number of protons, which is the same as the atomic number, right? So if we want to find neutrons, remember you take the total number of nucleons and subtract from that the total number of protons, and that gives us 146 neutrons in uranium-238. Okay, so let's talk about the nucleus and the forces that are at work within that. Okay, so you've got in this small area, remember a nucleus is super tiny, right? Even though it contains all the mass in it, it is almost infinitely small. Okay, so you've got neutrons and you got protons. So the nuclear force, or what's called the strong nuclear force, okay, holds all of these things together. Okay, it's one of a fundamental force in the universe. But we also have this issue too, another fundamental force, which is the electromagnetic force. And since we have protons, which are the same charge, they are repelling each other. So these two forces are in conflict in the nucleus. Okay, and so a lot of this comes into play with instability and radioactivity. And so we'll talk about that and look at the balance here. So part of the issue, part of it is this, you guys, is what's called binding energy. And you may have seen that at the bottom of the last slide. So binding energy, you guys, is kind of like, remember when we talked about potential versus thermal energy in chemical bonds, right? Potential energy is basically how far apart things are. The farther apart particles are that are attracted to one another, right? Okay, the more potential they have. Okay, and then when they come together, they release energy, and that's kinetic or thermal energy because it becomes like heat. So when we talk about binding energy is the total energy we need to put in to pull a nucleus apart. Okay, so the total energy required to separate a nucleus into individual nucleons, which is quite a lot of energy, right? Or if you flip that around, it could also be the energy that's released when a bunch of nucleons come together and bind to form a new nucleus. Okay, so it's either one of those. All right, and then just to kind of put it into perspective, binding energy per particle, that means the total binding energy divided by the total number of nucleons. Okay, so we can look at it and say, okay, how much energy is it to just pull one particle out of that nucleus? And that'll come into play here as we start talking about fission and fusion down the road. Okay, Now let's get into radioactivity and an unstable nucleus, okay? An unstable nucleus undergoes a change and a reduction in energy to become more stable. So what's important to stability is this: you have protons and neutrons. What's the ratio? And really the kind of the working theory is, why do we have neutrons? Why do we have these particles that have no charge? What's their purpose? Well, we think one of their purposes is to reduce repulsion. They kind of act like a buffer between those protons that are in a nucleus and allow that electrostatic repulsion to be reduced so that the nucleus doesn't just fly apart and the strong force can hold it together. Okay? Now, one thing to know is this: the larger a nucleus is, the lower the binding energy per particle. So large nuclei are much easier to break apart than small ones. So like take, for example, a helium nucleus. Man, that thing is tiny. It's got 2 protons, 2 neutrons in it. Is not much that's going to blow that apart. But if we take something really large, like a uranium nucleus that has up to over 200 different nucleons in it, it's much easier to begin to split or break apart that nucleus because it has a lower binding energy per particle. All right, so what makes things unstable? What makes nuclei unstable? Well, there's really, I believe, 3 reasons, okay? Really, actually, there's 4. You got too many neutrons, okay? That would be one reason, okay? You got too many protons or too few neutrons, okay? So this is kind of the same thing, same issue, right? Okay, but 2 different ways to look at it. And then last but not least, you have a nucleus that's too large. It's got too much stuff in it to hold together. And really, when we talk about that, elements with more than 83 protons are unstable, okay? Really, the largest 2 nuclei that are stable are lead and bismuth, which are elements 82 and 83. Okay, anything bigger than those pretty much can guarantee you is radioactive. All right. Oh, by the way, here's some uranium, right? Remember, it's element 92. That's just some uranium ore there. All right. So this graph here is important, and really in a couple of slides here, it's going to become even more important. So what makes things stable? All right, so we've got this graph here of protons versus neutrons. Remember, that ratio is really important, okay? And if we notice, when we're down here with smaller nuclei, they have a 1-to-1 ratio of protons to neutrons. And then as the nuclei gets larger, that ratio gets larger, where we get up to a ratio of 1.5, 1.5 neutrons almost to every 1 proton. Okay, so why is that? Part of that is because as you get larger, right, you need more buffer in order to keep all those protons separated so that the electrostatic repulsion isn't too much, right? Okay, and then smaller ones, smaller nuclei, that's not as big of an issue. Okay, remember this: once we get up here, you know, beyond 80 or so, 83 protons, okay, then we get too large. Okay. Anything that's outside of this little zone of stability here, right, tends to be unstable and radioactive. Let's look at this in a little bit more detail. Now, what happens if you're outside of that zone of stability? Okay, it means you're going to undergo, or the atom is going to undergo nuclear decay. So there's mechanisms in order to achieve stability. And those 4 mechanisms are this, right? Alpha decay, beta decay, positron emission, and electron capture. Those all sound pretty cool to me. I don't know about you, okay? But we're going to kind of cover all 4 of these just real quickly, and then we'll look at some other things, okay? So here we go. Again, back to this graph, okay? This is a really important graph. Now we start to see how this graph gets filled in, right? We've got, if you have too many neutrons, right? If you have too many neutrons, you're going to undergo what's called beta decay. And we'll talk about that in a sec. If you have too few neutrons or too many protons, you undergo what's called beta plus decay, which is positron capture, which is positron emission, or you do electron capture. Okay, and we'll look at those, and there's a slight difference between them, but it results in a similar a similar outcome. And then last but not least, if you're too big, if you're an element that is too large, bigger than 83 protons, you undergo what's called alpha decay. Okay, and that means the nucleus is too large. All right, so I think I'm going to stop this video right here, and we'll do a second one attached to this, because I have a 15-minute limit on these videos, and we're already over 10. So tune in for the next video. It'll be attached on the same announcement in the stream for NuclearChem, for AP Chem. All right, thanks you guys. See you in a bit.